let's get started. So, first, projectiles. What is a projectile? What is a projectile, right? The most basic thing to ask, kind of like, what is the answer to that, right? What is it by definition?
Something that has an initial velocity, like in the horizontal direction.
Okay, at least it has to have initial velocity in one of the directions or something. Now, what else, Ken?
It's influenced by gravity, like because it's in a free fall state.
So it's an object that has initial velocity but influenced only by gravity. Only by gravity. It's not going to be worrying about air resistance right now. We're going to see the concept of air resistance later in the year when we get to forces and we'll look at derivatives with air resistance, which is really kind of cool actually. But even when we get to air resistance, it'll be one-dimensional drops. It won't be projectile motion with air resistance. So for the sake of this course, when we talk about projectile motion, we're really looking at two-dimensional motion. Two-dimensional motion only under the influence of gravity. Only under the influence of gravity. So yeah, these are like free fall problems, right? But we just had to give it a little push. Maybe give it a little bit of a push. So I don't know if you did this or not last year, so I'm going to assume for the moment that nobody has done it, but I know that some have. If I were to push a tennis ball off this table and at the same time drop a tennis ball at the exact same moment, do we remember from last year what happens as a result of that?
They land at the same time.
They land at the same time. Okay, so let's quickly just reiterate that so we can start by seeing this. So let's draw a little cliff, and let's draw an initial velocity vector from this cliff. And then let's take a second object and place it right here. And we'll say that its initial velocity is 0. Okay, the first one only has velocity in the x. So the black object is fired left or right, doesn't matter, but horizontally. And the red object is dropped. And yes, exactly what Matt said a moment ago happens. As the object in black starts to move in this parabolic fashion, the object in red falls at the exact same rate. So what's the difference? What's the difference? Chip?
The object that was pushed off has a component of velocity in the horizontal direction.
And therefore it has a component of also?
Displacement
In the
horizontal direction.
Very good. That's the only difference right there. They both cover the same delta y. They both have the same vertical displacement. It's the horizontal displacement that differs. So this is problem type number 1. Horizontally fired projectiles. Horizontally fired projectiles. What's the initial velocity in the y direction for both of these projectiles? 0. 0. Again, a free fall, you know it's 0. And then again, if you kick something only horizontally from a cliff, like a pebble off the top of a building, it is launched outward but not at an angle, and therefore vertically it is not moving for that instant in time before it begins to fall. Okay? So they both, what have in common is that v0y for object 1 equals v0y for object 2, which equals 0. Okay, that's the key to this problem. That's the key to this problem. And I'm calling it 1 and 2 now just arbitrarily. It doesn't matter which is which in this case. All right, so that's the idea of horizontally fired projectiles. Now, with that, we want to also take a look next at the concept of velocity vectors. Velocity vectors. So along the path of the projectile in black in this diagram, what can you tell me about the velocity vectors at each of the 4 instances? What can you tell me about the velocity? And I'm saying vectors because we're going to have both horizontal and vertical components. But what can you tell me about each horizontally and vertically at each instant in time? At each instant in time, what can you tell me about those velocity vectors? What do you see happening? Okay.
They're increasing.
Which is increasing? Think about which is being accelerated. Are you accelerating up and down, or are you accelerating left to right? What causes acceleration? You're on the right track, Kara, but get a little bit of help. Let Chris help you a little bit. Go ahead. Only the vertical. Only the vertical. Because what's causing the vertical velocity to change? Gravity. So the vertical velocity becomes greater as the object falls further down. What about the horizontal? Like, only the vertical, what can you conclude about right? Using deductive reasoning. Chip?
There is no change.
There is no change. Very good. So look at the length of the vector in the x direction. I'm trying to draw it the same each time. I'm trying to make it obvious that Vx is a constant. Vx is a constant. Okay? Now, Vy obviously gets greater, but greater in the negative direction. So, multiple choice, right? Just like you just took that quiz, multiple choice. Speed versus velocity. Talk to me about this projectile. And use speed and velocity and give me some sort of analysis of the object's speed / projectile velocity in the vertical direction. What statements can you make, Max? Go ahead. Nice and loud.
If you designate down as negative,
I like that. Okay.
The velocity is becoming more negative.
Okay.
And the speed or the magnitude of the velocity, because they're the same thing, is increasing.
Very good. So when Max says that the velocity is getting more negative, he could also say that the velocity is decreasing, which sounds wrong. It sounds wrong literally to say that. But by you saying decreasing, it simply means becoming more and more negative. Remember that. Velocity decreasing means it's just becoming more negative. So if it started at 0 velocity, which it did, it becomes negative. Maybe 2, then negative 5, then negative 7. It's becoming more negative, and therefore its value is decreasing. Negative 2, negative 5, negative 7. While the speed, as Max said, is increasing. And what we can say about the speed is that it's increasing in the negative direction. That's okay, we can say that. The speed is increasing, but it's moving in the negative direction. So would this object be accelerating or decelerating?
Accelerating.
Which one?
Accelerating.
Yeah, even though it's negative acceleration, it is definitely accelerating. What does decelerating mean again? What does it mean to decelerate?
Slow down.
Just slow down. Very good. It doesn't mean that your acceleration is negative or positive. It simply means that the acceleration opposes motion. Slows down. If I'm moving this way and the wind is pushing back, that's deceleration. If I'm moving this way, this is like terrible, like a cartoon, and like imagine you had like a rocket or you would fart enough, you would push yourself forward. I know that sounds ridiculous, but think about it. For every force, there's an equal and opposite force, right? So any sort of thrust this way, which is what a rocket is, or a fart is, when you think about it, it would propel you forward. So that would be acceleration because it's helping my motion. So yes, speed is increasing and it is accelerating downward. Okay, very good. Now, this is the first case. Let's look at the second case now, please. So case 2, and the first one I had to put it on a cliff. Case 2, I don't have to put this on a cliff now because now I'm not launching horizontally. I'm on the ground and I'm going to talk about an object that's launched at an angle now. Again, if I'm on the ground and I'm launched horizontally, it's just x direction. It's one-dimensional kinematics. Right? If I kick the soccer ball on the ground and don't get under it at all, the ball is going to stay on the ground the entire time. So horizontally fired projectiles from the ground don't make sense. They just become one-dimensional motion. Right? If I kick this guy right here across the room, that's just 1D motion. It's a horizontally fired projectile, but it's not even under the influence of gravity, right? So this is not really projectile motion. But if I were to hit it horizontally from here, then it's projectile motion, because I'm giving it a starting height. Now, this, though, from the ground at an angle, is indeed projectile motion. So let's denote that angle as theta right there. Let's recall from vector components, from vectors, and from last year and from the start of this year, what our two components are. How do we find the components in the x and the y direction? What do we use? What do we use for the x direction and for the y direction? If you forget, remember it's alphabetical, by the way. It's alphabetical. You could remember that. Max?
V initial times cosine theta for x, and then the same thing with sine for y.
So x comes before y, cosine comes before sine. Okay? Or from your calc or your pre-calc, you should know by now that the x component on the unit circle always came from the cosine, and the y component always came from the sine. So all that unit circle stuff that you did, right, that comes back to play a role. Now, those are the initial velocities in each direction. What did we say a little while ago, though, about the x direction? Specifically about the x direction. About the x direction. It doesn't change. So what else could I call this? Instead of v0x, what could I also call it?
V of x.
You could just call it vx. Or if you want to even call it something else, you could also add, when something is constant, its instantaneous is equal to its average. So you could call this average if you want as well. Remember that idea, man. When a velocity is constant, its instantaneous velocity at any moment could be called average velocity. Okay, so I don't have to call it v0x, I can just call it vx. If you want to call it v0x, by all means, call it v0x, that's fine. Okay, but recognize that the velocity will not change in the x direction for projectile motion. So, as a result, what one formula can I use for the x direction for projectile motion problems? What one formula can I use? Think about your big three we went over last week. Remember we derived them all? Or we actually, that was honors we went over. Think about your big three formulas that you know. And think about the fact that acceleration equals. So two of those formulas do nothing for me. Vf, or V equals V naught plus AT. If A is 0, it just tells me V naught equals V, which also illustrates that it's constant velocity. If I have V squared equals V naught squared plus 2AY or 2AX, that 2AY or 2AX drops off. So you get V squared equals V0 squared, again, illustrating that the velocity is the same in the beginning and the end. So those two formulas we've got to throw out the window. We can't use them for the x direction. Max, what's the formula we can use?
Delta x equals x initial plus vix.
Yeah, so we have this one right here, and we're going to drop off the last term. So this is the formula that we can use in the x direction only. So let's jot that one down here. Okay. And again, V0 in the x direction is specifically V0x. So let's start using double subscripts where possible. So this will become x equals x0 plus V0 cosine theta times t. Again, I'm simply replacing the definition of V0x with V0 cosine theta. Let's circle this, box it, whatever you want to do, but this is the only formula you're going to use in the x direction. And then in the y direction, we've got all three still. Okay, we've got all three. I'm going to quickly jot them down so you can remember them. We've got y equals y0 plus. Now watch what I'm going to do. Whenever I put v0y, I'm just going to put v0 sine theta. And what am I going to put for a? What could I put for a? What other letter that represents the acceleration? What letter do we use? Yeah. So some textbooks, which like yours, like to do this. So instead of putting a for acceleration, I'm going to put g. And g in this section is negative 9.8. Okay? So instead of a, I'm putting g now because we're looking at vertical motion. The second equation is this. And the third equation is this. So those are the three equations that we already know, but now we're just looking at them in only one or the other direction. These equations, believe it or not, are technically coupled though. They're coupled, meaning they actually do affect each other. What variable is the linking variable in these equations, or what variables, I should say, because there are more than one. You had me last year, I always said there was only one linking variable. There's actually 2 or 3 linking variables, really. Okay.
Gravity and initial velocity.
So initial velocity for sure. Gravity, no, because there's no gravity over here.
Oh, I'm sorry.
Yeah, all the equations, right? All of them. So initial velocity is in all of them. I agree with that. Agreed. Yes, what else?
Time.
Time is the one that's the most important because the time it takes to fall is the same in both directions. Time is in all of them. And what's the other one? There's one other variable. Theta. V naught, theta, and t are all variables that we could solve using most likely substitution method. If I need to find time, I can substitute in for theta another equation to get time maybe by itself. And we're going to get into a lot of these examples so you can see them more, but I want you to recognize that just by inspection, just by looking at these equations. Okay, so the one in red and then the 3 in blue over here. Any questions on this idea? I'm going through it obviously much faster than I would in a regular physics course because you have seen this idea already. When we get to the problems, I'll step through them a little bit slower. Okay, now to see this, and what I like that your text did, this is on page 71 of your text on the next slide here. Look at this next figure here. So I want to discuss this idea for a little bit. So what your text does, and I'm trying to, I want to see the first one here. Okay, perfect. What your text does, and this is again right out of your textbook, is illustrates projectile motion as the sum of vertical plus horizontal motion yielding projectile motion. And that makes sense to think about. If something is moving as a projectile, it must be moving vertically and horizontally at some point in time. Maybe not right away. If I kick horizontally, in the beginning it's only horizontal motion. But eventually, it falls in a parabolic path, and it travels both in the x and the y direction. So here we're noticing that initially, this object, take a look at it, is fired in both the x and y direction, right? It's at an angle. So look, in the beginning, my vertical velocity has a component, and so does my horizontal. And together, those equal this vector right here. How do I ever get my overall velocity? Use what theorem? Every time. What theorem do I use to get the overall velocity if I'm ever trying to solve for it? How can I find for it? Pythagorean theorem. It's always going to be vx squared plus vy squared equals the velocity squared. Every time. We've done this already. We've talked about it already. And theta again, it should be instantaneous, these answers. Theta, how do we get theta for all these problems?
Just
Subito, very good. And what specifically, what function does it always become?
Tan -1.
Tan inverse of Vy over Vx. Assuming we have Vx and Vy is what I'm saying here, right? That's how we always get back to our velocity. At any moment along the way. So let's look at the second instant in time now. In our second instant in time, the projectile is now here. Take a look at it, please. So when it gets to here, its horizontal velocity doesn't change. So look at the length of the vector. It hasn't changed. But the object has physically moved. The object has also physically moved up, but look at the velocity. The velocity was pretty big in the beginning, and now it's smaller, because acceleration vertically is slowing it down. So we see the vertical component gets shorter, the horizontal is the same. Well, if one of them gets shorter, then the overall velocity must also get smaller than what it was in the very beginning. So this is like a time lapse of what we're seeing here. In the third instant, we're going to be at max height. And this is probably our most important one, and you know this by now. At max height, vertically, what does it do? Vertically, it stops. At max height, it's going to get up to the top, and it's going to stop in the vertical direction. So Vy is 0 when it reaches the top of the path. But it is really important to remember that it is still moving in the x direction. This is a common mistake. A common mistake is that students say the overall velocity is 0 there, and that is not true. Remember, if it's a projectile, it's always got x velocity. If I'm just tossing an object up and down, though, then at the top, it physically has 0 velocity, if I'm only tossing it up and down. But the minute I throw it at an angle, at the top, it still has horizontal velocity. And on the way down, we'll see exactly what we can expect. Again, what we saw already with the horizontally fired projectile 2 slides ago, the velocity in the y direction now becomes negative. Thus, its speed is increasing, but in the negative direction. The x is still the same, it doesn't change. And now look at my overall velocity vector. It's now southeast, because it's moving down and to the right. But here it was northeast, because it was still moving up and to the right. At the top, the velocity vector was only east. It was only east. Okay, and the last part, obviously, is we're going to be continuing toward the ground. And if we want to find the impact velocity here, the impact velocity, remember the phrase impact velocity. It's not actually the velocity after impact. It's the instant before impact. Before impact. Because after impact, it's going to stop. So that's like a common thing in regular physics. Students say, oh, it's 0 when it hits the ground. No, it's the instant before it hits the ground. That's what impact velocity means. And that's this value right here. This overall hypotenuse, this vector, would allow us to find the impact velocity. Now, yeah.
If this is kind of like a little detail, like say it bounced off the ground, then like how would you be able to use like a similar process?
If there were no energy losses at all, which is not the case ever, it would take the exact same path every time. Exact same path every time. But what do we know? We know energy losses occur on collisions. Yeah. Conservation of momentum holds true, but conservation of energy doesn't hold true because of inelastic collisions. Elastic collisions, conservation of energy holds. So this would do this. Okay? But it would still be parabolic each time. And the angle that it would launch at, theta, that it started, would be the same for each successive bounce.
How would you
but
find
that
the
match
velocity?
It wouldn't be, you'd have to be given more information about this problem to find it. You're asking in general?
Well, like, so you probably have to know like the elasticity.
You mean of the next bounce you're asking?
Yeah.
Oh, yeah. For the next bounce, you have to know how much energy loss there was based on the collision, and then you probably want to use like kinetic energy instead of kinematics. Work energy. I would personally do that. I think it'd be a lot easier to do it this way. But the idea, though, Matt, is that again the angle is the same. It's just that you have a less velocity, which means the max height will be less each time. Yeah. It's not there. The bouncing ball. I don't know if you guys did. You guys do anything with like a tennis ball last year in honors? If you drop like a bouncing ball or a tennis ball, what's going to happen each bounce? And that's exactly this. We talked about it last year. What was it?
We used vernier.
Did we use vernier last year? Yeah. I had and the bouncing ball would successfully get lower, and it was called the restitution of, or the coefficient restitution or something like that? Is that the right phrase?
I think so.
Same thing.
Elasticity
Coefficient of elasticity? Why do I think what is restitution? Where did that come from? It's in physics. Is it the same thing? It has to do with pretty much the elasticity of the ball and how much energy it's going to lose proportionally each time based on what height it gets to. If you get to half the height, how much energy you lose? Half your energy. Right? Think back to potential and kinetic. I'm getting ahead of myself for kinematics. But for energy, it's very useful. You're going to notice on the AP exam, when you can use energy, use it. It's a lot easier to do energy method with projectile and potential and kinetic and work done by friction than it is to do it with kinematics. Is that clear what I'm saying? Okay, you're usually only going to be looking at resistant forces when it's a drop, not projectile moving. Okay. Now, let's take a look at an example real quick, and I want you to think about this for a moment. Okay? So this is a blow dart. I know it looks like a funny diagram, right? So this person's like, you ever seen that with the straw? Anybody ever seen Ace Ventura, Pet Detective? With Jim Carrey?
I've seen it.
It's an Nolan movie it is. Anyway, yeah, all these movies that have blow darts and stuff. They use on animals to tranquilize them. So this is a blow dart. I don't know why, but it is. And there's a can, and the can is attached to the ceiling with a mass M. That can is then dropped. Okay, the can is dropped, but the projectile is aimed at the can. It turns out, get away, I guess. It's hard to, I'm trying to think of a way to lead you into this idea. Well, it turns out here in the diagram that what's going to happen. It's going to hit the can, right? What if I just blow the air dart faster and give it more initial velocity? What do you think will happen then? Say it? Alright, so what if I go versus? What's the difference?
Just hit it at a different spot.
Ah, very good. Right. It just hits it at a different location. It's really interesting, actually. This is a phenomenon. It's not a phenomenon. It's physics that teaches to us. But this is interesting that people don't really recognize. We don't have to get into the mechanics behind this today. But I want you to recognize this because this could be a very easy multiple choice question on the test. This is a classic problem where your trajectory without gravity affecting would hit the can. But gravity affects your blow dart and the can both equally, right? So as a result, it's not going to hit the can where it's stationary, it's going to hit it as it's moving. But if you blow the blow dart faster, it's just going to hit it further up here. If you blow it slower, it's not going to reach as high as a peak, and this is going to have more time to come down, and then they might hit here. If you blow it really slow, it might just hit it right before it hits the ground. If you don't blow it fast enough at all, it won't even reach the can, and it'll land here. So your initial velocity will dictate where it will hit the can. Theoretically, if there were no ground here, it would always hit the can. Even if you blow it with almost like 0.001 meters per second, it would go like this. And eventually, somewhere down here, you'll hit the can. I know, right? Isn't that crazy to think about? But it is true. Okay.
You have to drop the can as you blow the exact same.
Absolutely, absolutely. It's got to be instantaneous. It's got to be simultaneous. Yes, absolutely. Yeah.
Is that assuming that there's no
Air resistance.
Yeah. So in real life, it wouldn't really.
No, that's why this isn't even a good lab one to do because it won't work. You could try it. We could try it technically with so I have a projectile launcher in there I used last year if you remember my class. I'll probably use it again. It's pretty cool. You could set the angle. You could measure the initial velocity with the photo gate in there. You could change the pressure of the line. You could measure the time by laying the time with that. It's really cool. It's advanced. I only have one of them though, so I do it as like a class thing. But we could use that theoretically and try to drop something, but the timing piece is the hardest part. To get this to be dropped at the exact moment is really tough. And then on top of that, it would have to be a big enough object that it actually, you have a little bit of room for deviation.
Yeah.
So maybe we could think about doing that. Maybe I'll see if Alex wants to create something over the weekend that can do this. But the idea behind it, I want you guys to get and see here first. So far, so good? All right. So what I'd like to do is get into two equations that will be useful in this section. Now, I'm going to write the pages that they're derived on. There's no need to derive these equations because this test is a full calculator active test, and these equations are not on your formula sheet. What can you do with them? I'm being honest. What can you do with them? What should you do? Yeah, store them somewhere. Store them somewhere. These tests nowadays in AP, this is not, when I took the test, it was considered cheating by the way to do this. Putting programs in your calculator was considered cheating, and teachers and proctors would have to go around and clear the RAM of every student's calculator. Then students realized you could archive the programs and it would clear the RAM. So there were all these workarounds. So over time, AP realized, this is stupid. Let's just assume any kid can write whatever they want on their calculator, but we're making the test so hard that if you have to study on your calculator and look it up every time, you're never going to finish the test. That's their mentality. So you can't put every chapter in your book, but certain formulas, I absolutely recommend you put in your calculator. These ones I'm going to show you, you should. Is that clear what I'm saying right now? It's not a form of cheating. They're assuming all students have equal access to a calculator. So take advantage of it. It's like if the rules aren't written a certain way, bend those rules for yourself, right? So here are the two formulas that you're going to want to jot down. The first one comes from combining our two position formulas. So I'm not going to do it, but I'm going to show you. So if I take this formula here, and then I take this formula right here, and if you want to, maybe for your own practice, you can try it yourself. You don't need to, but you're welcome to. Okay, if I take these two formulas and combine them by solving for t in the first one, and then plugging it in there and there, what does that do? If I solve for t in one and plug it into the other, what am I effectively doing to my resulting third formula? What am I yielding? I'm yielding a formula that doesn't have time. It doesn't have time. Think back to substitution method. In calculus this year, you're going to do it a lot. When you get to optimization, it's going to come up in chapter 3 toward the end. When you get to optimization, you're going to solve in terms of x for y, you're going to plug it in, and that eliminates one of the variables. Elimination method, substitution method, they're kind of the same thing actually, but one assumes the functions are all linear. Because these are not linear, we can't use elimination method. Remember elimination method in math? Adding the rows together or subtracting the rows. So we're going to use substitution. And this, as a result, yields a third equation that eliminates time as a variable and allows us to have the position y as a function of the position x. This is the resulting equation you're going to want to jot down. That's 10, yeah. Okay? This is the equation you're going to want to write down. This is really useful. If you want to know the x component and you know the y, meaning displacements are. If you want to know the x displacement and you know the y, or vice versa, and you know nothing about time, this is an equation that eliminates time altogether. Again, an equation that solves for y as a function of x.
Would you suggest a program and or a calculator to just write it in?
I would just write it in. But what do you mean program it? So that you could like type A, B, C kind of thing? I wouldn't go into that much detail. I would just have it in your formula, in your program somewhere as just text. Come up with your own nomenclature. Like there's no equal sign, I don't think, or there is, but you do it in math. I used to use a colon when I meant equals on my calculator. When I would put things in a program, I would use a colon because a colon is on a keyboard. There's an equal sign, but you gotta find it in like math, logic. It's really annoying to do that. So when you're gonna type this in a program, and if you don't know what I'm saying right now, feel free to ask me, or just go to YouTube and say, how do I type in text into a program to save? I guarantee you there's 1,000 videos on this. But type it into your calculator the way you would see it. Yeah, Spence.
How did you get the
So you take this equation here and solve for time here and then plug it into the second. This is on, just so you know.
Is it just for y or is it also for x? Is it a different equation for x?
Say again?
Is it just only for y?
Well, technically, to get the x equation, you have to solve for x, but look where it is. It's in 2 spots.
Yeah.
So if you want x, you plug everything else in, and then x becomes a quadratic to solve.
Okay.
So if I had this number, this number, this number, this number, it would become some number equals some number x minus some number x squared, and then use the quadratic formula to get x. Okay? Guys, this is on, just so you know, page 72 in your text. The derivation. Now, the second equation is called the range equation. And I guess technically that's the x equation you were asking about, Spence, right? You said x? Yeah. So the second one is called the range equation. I personally don't love the idea that they call it r equals. So I'm going to write it a little bit differently than your book has it. Okay, so this is what I would write it as. Okay? Again, the book uses r equals, which is fine, range. Range is really horizontal displacement. So I'm going to call it x minus x0 instead.
So it's range as a function of displacement rather than distance.
It's range as a function of actually not displacement. There's no y here at all. So this is not as a function of y. This is the range as a function of initial velocity, the angle, and gravity. There's no y variable in here at all. But this is the vertical displacement as a function of the horizontal displacement. And other things, obviously, as well. Again, these are functions of several variables, is what we note. Now, answer this question for me. You learned this last year. What angle gives you max range? 45, right? We all know it. 45. Now, can you see why it is now? Who can explain why it is now? Chip?
Because if you're firing it at 45 degrees, you are optimizing the horizontal velocity and the. Well, because if you
You're answering based on last year. Based on what I just wrote you.
Okay.
You're totally right. You're totally right. But my question is based on what we've just written on the board here.
Because sine 90 is 1.
The sine function is the maximum when the angle is 90, right? Sine of 0 is 0. And the sine function, if you remember, looks like this. The sine function starts here and rises up. And this is 90 degrees. And then it comes back down at 180 degrees. Then it loops around until 360. So sine function is maximized when the angle is 90. Well, I just said 45, but look, the angle is a double angle formula. That's why. You're totally right, but mathematically is my question. So when we want the most range possible, we set theta equal to 45, which makes this number equal to simply 1. The sine of 2 times 45, or the sine of 90, is 1, and therefore, this gives you max range right there. V0 squared over G is max range. So maybe as a third formula, you might want to jot that last piece down, right? And if you want to, you could also write max range equals this. Okay, and this is normally just range, and this is y versus x. So those three formulas are not on your formula sheet, but can become useful. You don't want to spend time on a test having to derive them, because the test is time. So know what they are and put them in your calculator. Okay, have them written down. Utilize them. Utilize them.
They don't give it to us?
No, it's not on your formula sheet. Your formula sheet only gives you, and I have it right here actually. Let me see. I think it's just the big three. Yeah, just the big three on the formula sheet. Nothing beyond. The formula sheet, Max, doesn't even talk about the y direction. It assumes you know that you replace x with y and you replace a with g. Like those are the formulas up here. See these here, like this last one? This is not even given on the formula sheet. It's given in terms of x. So the formula, the notation is that you know that horizontally and vertically they behave similarly. Okay.
So what's the difference between the
Got it.
range and the max or range?
So this will give you the range for a given angle. So if the angle is 30, 20, 15, you can get how far it's going to go. But if you want to get the max range, you should remember to set it equal to 45, and sine of 90 becomes 1. So that just becomes a 1 right here, so I don't need it anymore. So this is a special case of the range function. Yeah? A special case of the range function. All right. We should quickly just discuss in general, what would air resistance do? This is multiple choice, conceptual. Theoretically, what would air resistance do to both the range and the vertical displacement? Remember, range in physics means horizontal displacement, not like domain and range. What would air resistance do to both the range and the vertical displacement? What would it physically do? Use logic, use common sense. It's not math involved here at all, right? What happens as a result of air resistance occurring? Chip?
Well, in relation to like the vertical and time, so it'll spend less time in the air.
Agreed.
Because there's air resistance, so there's like an additional force. And since the y direction is directly related to time, it'll be the object will spend less time in the air.
Good. And therefore, if it spends less time in the air, what else can we conclude?
They'll both decrease.
Both the vertical displacement and horizontal will go down. So, when air resistance is accounted for, both or all three, T, delta Y, and delta X go down. How far? We can't answer that. We can't answer that generically. We can answer it for specific problems, but we cannot answer that as a general answer. But they will all decrease. This is again assuming that air resistance is a resistive force. If you have wind that's lifting you up, then it's a whole other ballgame. It would actually be helping your motion. Next.
Delta Y won't actually go down because it'll just stay there. But the delta Y from
Sorry, yes. That's a really good point that Max just made. If we launch from the ground, really good point, Max. If we launch from the ground and end on the ground, delta Y is 0. Y max would go down. Very good. Y max. So yeah, the maximum Y height will definitely decrease. Good point, Max. How about this? Air resistance. Air resistance. On the way up. On the way up. Air resistance helps gravity. Think about it. Think about it. Right? On the way up, gravity acts which way? Always. And which way is air resistance acting right now? But on the way down, yeah, isn't that funny? Air resistance on the way down actually slows the object down. It opposes the motion, but since the motion is down, air resistance is up, and gravity is down. Which is why eventually you can reach something called terminal velocity. A fun thing we're going to talk about soon.
The forces are equal.
When the force of gravity equals the force of drag, when they're equal and therefore constant velocity.
I was going to ask, would you say there's no air resistance at apex, or?
Did you say there's none at the apex? Technically, it's still moving left to right. So if it's a projectile, then it would still have some. If it were straight up and down, the moment it stops, you could say that air resistance is 0. Now, again, this whole thing is assuming there's no wind. Air resistance and wind are similar but different. Air resistance is a resistive force that's a function of your velocity. It's like this, right? Everybody do this real quick. Well, real quick, real slow, right? But then don't slap the person next to you. Then go like this. And you physically feel the air. The air resistance you feel, turns out, we're going to see this later. We're going to see this later in the year, but just to reiterate it, the air resistance you feel, force of drag, is proportional to the square of your velocity.
Well, that's why if you're in a plane, you skydiving, you're flying around the back.
If you're in a plane, say again.
If you're playing with skydiving, like when you jump out, air just pushes you so far away from the plane.
So yeah, because the plane is going like this, and then you jump out, the air resistance is going to oppose your motion this way.
That's the only force that you inside gravity.
And then once you start accelerating down, then the air resistance up gets greater as a function of the square of your velocity. This is the key, that's a square. It's not linear. It's not linear, which is interesting. So as you get faster, the air resistance increases, but as the square of the factor of increase of your velocity.
Your total velocity, do you feel like you're not neutral?
Yeah, you feel weightless.
Because what we feel is.
It's the equivalent of floating in a pool. When the buoyant force upward equals gravity downward, it's exactly the same. What is a pool? A pool is water. Water is a fluid. Air is gas. Gas is a fluid. Remember I talked last year about when you're standing here, you're really in a fluid right now. You are all submerged in a fluid. So when you're falling down, its air resistance is really buoyancy distance. It acts like buoyancy does.
Well, we feel acceleration, not velocity.
Would we feel acceleration?
No, what humans feel is like acceleration.
Correct. Because you feel forces, and forces come from ma. If you're on a train and you're moving at a constant rate the whole time, you don't even feel like you're moving. Try it sometime. Next time you're on Amtrak, is it smoother than a subway? Close your eyes for a little bit. You won't know if you're moving or not. If it's really running smooth, you might hear vibrations, obviously. But if you really took out all the sound and the car wasn't vibrating, you wouldn't know whether you're moving or not until the car stops or starts to slow down. Then you feel deceleration or you feel acceleration when it starts to take off. Now, yeah, you don't feel velocity, you feel velocity change, which is acceleration by definition.
It's like when you're on a plane, like in the air, like you don't really know.
Yeah, it's a great point. When you're walking on the plane and the plane is moving at a cruising velocity of 500 miles an hour, you can walk back and forth and you hopefully don't feel it. Hopefully. I know there have been other circumstances. All right. I want to do some things. How are we doing on time? Period time. 2 minutes? All right, that's okay for tonight. This is really important that we talk about all these ideas. So listen. Over the weekend, you guys have a good amount of work if you look at your homework notes, right? So, for section 4.4, if you want to, you could try to get a head start on like a homework problem over the weekend. Just to give it a look. You want to give it a shot of projectile motion. You could obviously do 4.1 and 4.3 at this point already. I think that's it right now. But I also gave you guys something else that's due coming up.
There's multiple choice, but that's not due.
Okay, yeah. So I think I put other like assignments and stuff on there. Let me just pull it up actually right now with you guys.